Hello and welcome to the third example of first order decay problems. In this third example, we are going to estimate the elapsed time needed to reach a certain concentration. Here's the word problem. Deltamethrin, a common pyrethroid insecticide, was misapplied to the lawn of the Boston Common. Not a great place for that to happen. The Massachusetts Department of Environmental Protection measured the deltamethrin level in soil of the common. They found a concentration of 133 milligrams per kilogram of soil. That's part per million. DEP has a health protective guideline level of 10 milligram per kilogram for deltamethrin in soil. So clearly the concentration they measured was higher than the guideline level. According to the literature, deltamethrin has a half-life of about 90 days in soil. So estimate when the deltamethrin levels will likely be below the guideline concentration, assuming no additional deltamethrin is added to the soil and the first order kinetic supply. Alright, we can do this. We're going to apply our first order decay equation. Let's just write that down. Ct equals C naught e to the negative kt. So we are interested in time. That's t, so we need to solve for t. So let's go ahead and rearrange this equation, solving for t. So you'll have Ct over C naught equals e to the negative kt. We'll take the natural log of both sides. Oops, that's not right. Got rid of the exponent. So the natural log of Ct over C naught equals negative kt, and t will then be the natural log of Ct over C naught divided by negative k. Alright. Do we have everything? Let's just double check. Ct, that's the concentration in the future. That's going to be our 10 milligram per kilogram. Starting concentration, that's the measured value of 133 milligram per kilogram. The decay rate, negative k. Let's see, we're given a half-life of 90 days in soil. So we need to calculate k. We can do that. 0.693 over the half-life. So plug in 0.693 over the half-life of 90 days. And when I did that, I don't have it. Let's just go ahead and do it. 0.693 divided by 90. So that is 0.0077 per day. So a little bit less than 1% per day, 0.8% per day. Alright, now let's go and calculate the time to get to 10 part per million. So we need the natural log of Ct, which is 10, over C naught, 133, over negative k. So where I did that, I get negative 2.588 over negative 0.0077. Remember, that's per days, the 0.0077, and I take the quotient, I get 336 days. So let's look at the interpretive question. Would prohibiting access to the common appear to be a practical risk management strategy? That would be, would prohibiting public access to the common? Probably not. It does not seem practical to cordon off the Boston Common for the next year. So some other strategies should be considered.